Hello. Today we're going to talk about deferred mortality probability, why it matters, and how to calculate it. So let's get started. Yep. Still fumble with this just a little. And let's go. Deferred mortality probability. Okay. So first of all, what is it? Now, I'll put it in actuarial notation. It's usually written Q with a X, and the preceding subscript would be something like A/B. Now, what it stands for is a probability that a life, I screwed that up, that a life age X lives A more years that is to X plus A, but does not live B years after X plus A. Okay, so so if you look at it in a little bit of a timeline, and let's say here's your life to age X, well, what this probability calculates is that your life lives to X plus A, but so this difference here, let's call it A, so this is A plus X, but does not live past A plus B plus X. Oh, I screwed that up again. A plus B plus X is what that is. So this distance, this number is A, and this number of years is B. Okay, so that's what it stands for. Now, it's an important concept in actuarial science, and I'll explain why in just a bit, but I think it would probably help to know how to calculate it. Well, one way of calculation is that if you use a survival function, and let's say the life starting at X has to make it A more years, so it's P sub X, lives A more years. So this has to happen, but then by the laws of multiplicative probability, this life now aged A plus X cannot live, has to die within the next few years. So it's multiplied by Q of X plus A, B. In other words, lives A more years after X, but dies within B years after X plus A. Okay, so that's one way of calculating this. Now, a second way of calculating this, just using survival functions, and we could do it this way, or you could say the person must first live, starts at X and lives to A, so that probability, but does not, you remove from this the probability that that same life starting from X makes it to A plus B. Now, it is a great exercise, and one I think every actuarial science student should do, is to show that these are equal. So show that these two are mathematically the same. Now that actually isn't hard if you decompose this part here this person lives to A, but then dies. But then at X plus A, now makes it to B. Well, that's hard to read, so let's just get rid of that. And I'll give myself a little more room. So this part right here, you can always write, makes it to A. Then, since we're calculating this, at X plus A, makes it to B. So these two things are equal. And then all you have to do is factor out this factor here from the side. So that's a great little exercise. So that's how it's calculated. Now to the real point of this video is, why do we care? Why is this important? And there are many, many applications. I want to give you one that my class is going to be coming up with pretty soon. But let's do a very quick review of probability. So a review of discrete probability density function. And let's assume that we've labeled the various events by 1, 2, 3, and such like that. So in this setup, I'm going to define P of K, and this P has nothing to do with this. This is probability. Is a probability that K happens. Okay. Now, if this is a true probability density function, and let's assume that our K, we're going to limit it to 1, 2, 3, 4, to integer values. Well, then we know by the definition of probability density function that the sum of K equals 1 to infinity of this thing here, just because it's a density function, they have to sum up to 1. And the probability of K, let's say, how could I say it? Let's use event notation here. So let P of K denote the probability that event E sub K happens. And then for K not J, we have to have that these things is the empty set. So this has to be a partition in your probability space. So we have to have that. Now, what's it have to do with our subject here? Well, let's think about Curtate life. And if we say that T sub X is the random variable that denotes, let's say years lived after age X, so that we can define this thing here, Curtate life. I'm going to define it this way. It's going to be this floor function, which is the least integer I should say the greatest integer less than or equal to T sub X. So let's say, and this isn't really that hard to imagine what it is. And I am going somewhere with this, by the way. So for example, let's say if T sub x is 42.8, then the curtate would be 42. Yeah, that's what we need. Integer part for, since these are going to be positives, you can just consider that to be the integer part. We're not going to consider negative lives, right? Negative lifespans. Now, what's the issue here? Well, the issue is suppose we have a policy that pays $1 at the end of the year of death. So for example, right here, so in this example here, if the person died at 42.8 years, the payment will be at 43, or it would be k sub x plus 1. Okay. Now, we're starting at life x, and let's say the person dies at t sub x, and this is a greatest integer before that. We skip to 1, and this is where the payment is. Now, because of the time value of money, we realize that the value of the $1 paid this far would be 1 over the interest, 1 plus the interest rate, raised to this integer power. And this integer power is going to be k sub x plus 1. And in actuarial science, this is commonly called V. So V is 1 over 1 plus I, okay? So given that this is now a random variable, we would like to calculate what's going to be the expectation of this, because we'd like to know how much money each policy is expected to cost the company. And 2, we're also going to be interested in the variance. That's going to tell us how much reserve we need for, outlier or unusual events, right? So in order to calculate these, we need a probability density function. And here, so here, we could say is that p sub 1 would be the probability of death less than 1 year. P of 2 be the probability of death. I said less than or equal to. Because at 1 year, you pay right at the moment of death. It goes down like that, right? So probability of death less than or equal to 2 years, but greater than 1. And so forth. Now you see where this is going. So if we get a probability density function and we want to put this in context, let's see what we have. Well, p sub 1, the probability of death within the first year, well, that's just this. The probability of death in the second year, meaning greater than 1 but less than 2, well, that's the probability in life age x. Now I'm gonna defy convention here and write down the ones. In actuarial science, you don't actually do that. But that's going to be 1 slash, and I'll leave the other one off. So life age x makes it 1, but doesn't make it the full second year. So life aged x makes it 2 years, but not one more, etc. So that this deferred mortality, and this just say that probability of life, of it being in the kth year, would have right here k minus 1 slash, right? Then 1 by convention. So you can see these deferred mortality things actually become your probability density function that we're going to be used to calculate the expectation, calculate the variance, and all this other stuff. So when we now go to calculate this, the expectation of paying at the end of the year of death of of a policy that pays 1 at the end of the year of death, that'll be this 1 slash q x b squared plus 2 slash q x b cubed, etc. And writing that in summation notation, we can see that it's going to be this. Better make sure that so let's go to k equals 0 to infinity. This would be to the k plus 1. And this, we're going to treat that as a 0 here. Okay. Slash, and we get that. So that is our factor expectation of this. Right? So you see the deferred mortality gives us that basis. And just to make it complete, like let's say we wish to calculate the expectation of this squared, because we might wish to eventually use the second moment to calculate the variance. Well, the beauty of that is all you have to do is square this. So it's really double the force of interest. And so double the force of interest is decorated by that 2. All right, so that is one reason that we are interested in deferred mortality. The other thing I'm not going to talk about in this little short video here is that this is for the payment of the policy. I mean, that what the policy pays out. The premiums paid, remember, are always paid by annuity due, which means you pay in the first part of the period. So if we wish to calculate the expectation of payments, we would basically be doing something like this, except we're starting with 0, and these factors here are going to be annuities of various lengths representing the annuity of the payments. So that's for a later time. But I just wanted to explain to you why, at least one reason why, this is such a fundamental building block. So thanks for listening.